Hello. Today I am going to derive continuity equation from Schrodinger wave equation. So before entering this derivation, I would like to address one point here. We can derive continuity equation, especially in quantum mechanics, three ways. One is from we can use non-relativistic Schrodinger wave equation by using non-relativistic Schrodinger equation. We can derive continuity equation. Another one is relativistic Schrodinger wave equation, which means Klein-Gordon wave equation. That maybe we'll discuss later uh, in relativistic quantum mechanics. So many basic topics are there still quantum mechanics. Another third one is we can derive continuity equation from Dirac's equation also. So Dirac equation is the very important equation. So please keep these points in mind. Continuity equation we can derive from three ways in quantum mechanics, especially the non-relativistic Schrodinger equation we can use to derive the continuity equation. Another one is relativistic Schrodinger wave equation, which means Klein-Gordon wave equation. Another one, third one is Dirac wave equation. So there is a significant difference between these equations. We will discuss this point later. First, we need to derive what is the continuity equation from the non-relativistic case. Okay. Uh, we already know what is meant by the uh, non-relativistic Schrodinger equation. This Schrodinger wave equation, which I am going to use here, especially the time-dependent Schrodinger wave equation. Okay. So let us take first Schrodinger time-dependent wave equation. First step. Okay. Uh, E psi equal to H psi. Okay. So put energy operator here. I H cross partial derivative of dou by dou t equal to, here the Hamiltonian operator, H cross square divided by 2m del square plus v into wave function psi. This is equation number 1. So I'm going to take here complex conjugate of this equation. Complex conjugate equation number 1. So complex conjugate of this equation, I H cross partial derivative of wave function psi complex dou t equal to H cross square divided by 2m del square. There is no change here. So here wave function you should multiply into the bracket. Okay, psi complex plus V potential energy V complex. This is the complex conjugate equation of the our non-Schrodinger wave equation. This is a non-relativistic Schrodinger wave equation. Okay. Now multiply this equation number 1 by from left side of the equation. I have seen this derivation many of my students they are unable to multiply this um, process, which is why I'm written here step by step. So in case if I say just multiply this equation, they are going to multiply here. They don't know which side they want to multiply, the right side or. So if you want to know these basics, please go and watch all the mathematical tools of quantum mechanics. Almost about 30 videos, all the basic topics of mathematical tools of quantum mechanics, which is the Dirac's bracket notations, unity transformations, Hermitian operators, operator basic principles. So many topics, almost 30 topics are there, 30 to 50 topics, basic fundamental information of quantum mechanics. If you don't know these notations, please go and watch the mathematical tools of quantum mechanics sequentially. Okay, you will understand the bracket notations, especially bracket notations. Dirac bracket properties are very, very important in quantum mechanics. So now multiply equation number 1 by from left side of the equation. Which equation? Equation number 1. This one. Okay. Equation number 1 by psi complex. Okay. It's better to write this one other letter wave function psi complex. No need to put here bracket. This is psi complex. Okay. We need to multiply psi complex from equation number 1. Okay, left side of the equation number 1. I h cross, because equation is minus I h cross operator. So before operator, this complex will give, and wave function equal to minus h cross square divided by 2m constant value. So before operator, we need to multiply complex conjugate of wave function. Then this is uh, space coordinate, right? So space coordinate in the form of a second order derivative is there. So therefore, it is better to write second order derivative in space coordinate wave function psi plus potential energy is nothing but scalar quantity. So there is no effect multiply like this. So why I am multiplying here only? If you know this property, Dirac properties, then you will easily understand this multiplication. Okay, slowly you will understand once you practice the Dirac bracket notations and properties, then you will easily understand these quantum mechanical notations. Okay, this is equation number 3. Now multiply equation number 2 by wave function psi. Okay, from right side of the equation. right side of the equation. Okay, let's go and multiply this equation right side of the equation. Uh, you will get this equation minus equation number 2, this one, right side of the equation. I need to multiply. So IH cross dou psi complex divided by dou t wave function psi equal to minus h cross square divided by 2m del square psi complex wave function psi plus v psi uh, psi complex. This is equation number 4. Now subtract equation number 4 from equation number 3. Okay, so please do this step carefully. Minus I h cross dou square psi divided by dou t complex wave function psi minus I h cross psi complex dou psi divided by dou t equal to minus h cross square divided by 2m dou square psi complex wave function psi plus h cross square divided by 2m psi complex del square wave function psi. So after subtracting, I got this equation. Then I am going to um, rearrange this equation like this: I h cross partial derivative of psi complex partial derivative of t wave function psi plus I h cross wave function psi complex dou psi divided by dou t minus, okay, h cross square divided by 2m into this one. I am going to write carefully like this: wave function psi minus psi del square psi complex equal to 0. So this I am going to give, this is equation number 5. This is entire equation number 5, this one. Okay, total equation, I mean. Now multiply this equation, equation number 5, divided by IH cross. Okay, you do this step after this step, then you will get this equation. So the whole equation we need to divide it by IH cross. So therefore we'll get psi complex divided by dou t wave function psi plus psi complex wave function psi dt minus h cross square divided by 2mi. Sorry, this is not h cross square, only h cross, because h is going to cancel, right? Okay. Next, psi complex dou square psi minus dou square psi complex psi. So this is the equation. If you carefully observe here, we have one equation, common equation, dou by dou t. This, it should be psi complex psi, okay, minus h cross divided by 2mi. I'm going to write this one delta outside the bracket. Remaining equation I should keep like this, minus wave function psi del psi complex. So here I did one mistake. Just wait. This should be here, right? Please go step by steps. Okay. So if you carefully observe here, two terms are there. One is time coordinate, another one is the space coordinate. So this time coordinate, we know very well known equation, this one, psi star psi is nothing but in quantum mechanics. What is psi star psi? Psi star psi is nothing but dou by dou t rho plus del dot z equal to 0. So we need to write this one more. One more step is there here. This one. So we should write like this. Okay, this one also correct, but just some simple modification is there. So by using these steps, we can identify our continuity equation from our derivation. 2mi delta psi delta. I hope you understand this one. Okay. Just I'm interchanging these portions and minus also. Okay, this is our standard equation. So this represented the, this term is represented the probability density. This term, I mean this term is represented the current density term. This term is the probability density term. Very, very, very important equation, this one. So this is known as the continuity equation from non-relativistic Schrodinger wave equation. So here the rho means, I mean probability. We are giving letter in quantum mechanics P, right? Let's go for P term. P is the probability. Psi star psi is nothing but probability density. What is difference between probability density and probability? So probability density is always positive. Okay, this is probability density. All these notations will help you solve the complex problems. Okay. Next one is very very important. J term, current density term, wave function psi, del, complex. This constant term, just I neglected this one. Okay. If you want to put this constant term h cross square divided by 2m also, that is fine. So these two terms represented, the one is probability density and one is current density. This one is the current density. These are the very very important. There is a slight difference is there, so which we'll discuss later. I mean in relativistic quantum mechanics. For now, this one is enough. Okay. So if you want more basics, please comment below. I'll try to explain one by one basics, especially notations, quantum mechanical notations. Why I am doing this series, especially um, mathematical tools. By using these basic tools, we can solve the complex problems. Okay, thank you.